Let me just sort of set the scene, if you like. So printed circuit board, you've got a number of reliability design questions that have to be considered. There's obviously the electronics reliability, the functionality of the printed circuit board that needs to be looked at. And that would be looked at by tools such as SPICE simulations, but also things like SI Wave, ANSYS's power and signal integrity tools. Potentially IcePack as well, which is a thermal flow management tool. So if you've got thermal flow or particular types of cooling, you might be using tools like that. And all of these different things have got to be considered when you're looking at a printed circuit board. But fundamentally, what you're looking at is, and what you have to consider is all of the impact that the environment is going to put on that printed circuit board. Now, that could be thermal change, not only through self-heating, but also through environmental heating, different temperatures and so on, where the board is going to operate, but also vibration and shock potentially, depending on how the board is used and where the board is sited and so on. All of these things are going to have an impact on the reliability of the printed circuit board. So what do we mean by reliability? So really, we're looking at the robustness of that printed circuit board unit to operate when it's subjected to thermal, mechanical, and vibrational effects. And that's it. I mean, that's really what we're looking at here, is the physics effects, as it were, on mostly on the solder joints, on the leads of components and so on as well, depending on the type of component, but also, and in particular, on the solder joints themselves. And so repeated expansion and contraction because of temperature changes, repeated vibration and shocks will all lead to stresses in the material of the components and the solder. And the solder is particularly the weak spot, because obviously it's what connects everything together and ensures that the component and the circuit works as it's supposed to. So we have to look at those aspects. And of course, as you know, when you develop a new product, you tend to use or do a lot of redesign because time is short. So you will take blocks of product that work and put them together into a new prototype, and it'll be built and it'll be tested, and it may fail in some way. And then there'll be redesign, reprototype, and so on. And actually, a significant proportion of a product's cost, a development cost, is lost in this sort of cycle of test, fail, fix, and repeat. And so what we really need to do is try and reduce that aspect of it and bring back the time that would be lost from that by looking at the reliability of the design early in the design phase itself. And this is where ANSYS Sherlock comes in. So as I mentioned earlier, Sherlock actually uses physics equations and materials knowledge to provide a reliability analysis of the design before you get to the prototype stage. So Sherlock looks at the mechanical shock, the vibration, and the thermal risk to the board, the components, and the solder joints on that board. The mechanically induced failures, if you like, the reliability of physics. And it builds on the information that's provided by the PCB design tools. And you apply the loading that you're going to see. So this could be loading that is that you would use on the shock tables or the thermal chambers, or it can be the loading curves of a typical cycle of operation out in the field. It could be a summer cycle, it could be a winter cycle, mixed, different types of environmental loading. And by putting this information together with the design, this enables the designers to make a decision early in the design process that could reduce these test cycles, and obviously ensure that the product is designed for the longevity, the lifetime that it's needed. So what Sherlock does is it provides a time to failure prediction for the components and the package and the board based on these calculations. And it displays this either in a set of tables or as a set of Weibull or life cycle curves, as you can see here. So the curves can be used for different loadings that are simulated, whether it's a thermal loading or a vibration loading, but you can get the overall module or PCB prediction as to whether it's going to achieve its life. So in this particular graph here, we have a lifetime expectation or a requirement of less than 10% of failures across 10 years of lifetime, let's say. If we do our calculations using Sherlock, and Sherlock is remember, it's using the actual physics, the nonlinear physics, the nonlinear material properties of the printed circuit board and the components to calculate how they will react based on the loading. We're not going to achieve that based on this particular design. We're only going to achieve maybe half that, 4.5, 5 years perhaps. Just to reference that to MTBF calculations, the MTBF calculations from things like the Mill Standard Handbook are based on a series of tabular results for individual components that are then linearized across a time period. And that doesn't really take into account the changes, the nonlinear materials, the changes in those materials based on the changes in the environment. And so the reliability of physics, understanding and analysis, which was developed some time ago, it takes that concept and actually brings it up into a much more sort of environmental and materials understanding of the problems. Now, Sherlock, I mentioned that Sherlock uses the PCB design tool data. So what we do is we import something like the ODB++ file from the PCB design tools. And this allows Sherlock to very quickly, within a matter of seconds to minutes, create a virtual 3D prototype of your printed circuit board with all the components on it in the positions they're supposed to be, all the layers of the printed circuit board and the connections. And then Sherlock then populates all of those components from its library. So we have an inbuilt library of hundreds of thousands of component models and also component templates, which are populated with data, material data. And then using this material data and this understanding and the 3D structure, this virtual prototype can be constructed really, really quickly. Now, if you were doing this using just standard finite element analysis tools in order to do it, to put it together, it can actually be quite a painful process because you have to build the design, you have to build the components, put the components on. It can take quite a while. So Sherlock takes that away from you and it enables you to do that literally in a few seconds to create this, depending on the complexity of the board, to create this 3D prototype. Once you've got that 3D prototype and you've populated it with all the different components, then you can actually run the analysis. And we have a number of different types of tools and analysis types built into Sherlock, which you can actually put onto the board itself. So you can do, in-circuit test analysis, where you might have a bed of nails or testing probes come down. You can understand the impact that might have on particular components and particular parts of the board. We've got plated through-hole fatigue, obviously thermal fatigue from on the solder joints, vibration, shock, and so forth. All of these can be applied to or tested for within the virtual prototype. What you see in the middle is of the screen is a way of bringing in the environmental loading that we're going to see. So this can be brought in through a series of curves, and you can have multiple curves depending on different situations, or it can come in through Excel style or comma separated value spreadsheets, which show the different loading profiles, and these can be the same profiles that might be used on your testers, your testing stations, or they can be loading profiles that represent the loading that the product is going to see when it's actually in its environment and working. And again, Sherlock not only allows you to understand the impact of this loading on the lifetime of the components through the Weibull curves and the tables, but you can also see the hotspots as shown by this sort of heat map type diagram. So you might be looking at the thermal response, or you might be looking at the vibration response to the on the printed circuit board, and you can see the areas where this might have the most impact. And this is valuable information that you can then take back into the design itself and understand, you know, how to fix this. And that actually leads me to a question, which is, when is the best time to use Sherlock? Well, actually, you can use Sherlock really early on in the design cycle. So if you have a handful of key components that you're looking to use to solve a particular problem, you know the sort of board material that you've got, you can actually put all of that together, and Sherlock will do, just from spreadsheets, a very quick analysis to understand whether there's a real difference between the coefficient of thermal expansion of the materials of those components and the proposed printed circuit board. And the idea here is that, you know, you're assessing to see if you're going to have issues later on. So perhaps you may need to change some of the components for a component, maybe go from plastic to ceramic. Maybe you need to change the material of your printed circuit board. And you can do this very early on, before you've really done any sort of main design. You can even have an early arrangement on the printed circuit board because of where the components are going to be, so you can put components on. You've got an outline of printed circuit board, and you can subject it to, you know, vibrational analysis and look at maybe where you put supports or do things like that. But at this sort of stage, this early stage, all the way through to the final sort of bill of materials and the final layout, the engineers that printed circuit board design for the long-term reliability of the design as you go through, and that's what Sherlock enables you to do. And then finally, you know, if you want to, as I've mentioned, you can look at the design for manufacture, so in-circuit test and so on, and solder reflow. Those can be considered, and the impact on the reliability of the printed circuit board from those aspects. But even later on, if you've got such a change management requirement, you've got a component that's gone obsolete, you need to understand whether the replacement component is going to have an impact. You can take that replacement component, the material data for it, drop it into your Sherlock model, run the analysis, and understand if it's going to have an impact on your reliability. So it's just to sort of summarize, Sherlock is a very simple workflow. You upload your ECAD design and apply and associate all the components with it. You apply your loading to the design, you simulate it, and you find any components that are not meeting your requirement or very close to failing on your board. And then you can start to mitigate and understand how you would improve that. And this is possibly best shown through a very simple case study. So here we have a printed circuit board. It's going to, in this particular case, it's a radio receiver. So most things are done by a single system on a chip, a very large BGA. The first thing that might get placed is the board outline might be restricted because of where it's got to go. There will be some key components such as connectors that have to go in particular places. And then the next big question perhaps is, where am I going to put my system on a chip? Now, the easiest place to put it would be bang in the middle of the board, because that's the best for routing to it, because it's a multi-pin module. So it's, how do I get all the connections to it? But how is that going to be affected if I then subject it to my reliability testing? So we can run a quick analysis, a shock analysis perhaps, on the board itself, and with initially placed components. And Sherlock will show us where the maximum stresses and strains on the printed circuit board will occur from modal shapes generated. And we can understand, where we're going to have problems. So we have a hot spot, as we might expect, in the middle of the board. And if we look at the lifetime prediction, we're not going to achieve our less than 20% of failures in this case over 10 years of life. So we now need to think about what we can do to mitigate these effects. So the design engineer, staying within Sherlock without having to go back and say, well, what if I just move my BGA over to one side out of the hotspot zone? So he can do that and very quickly rerun the analysis and see what happens to his lifetime expectation. The alternative maybe I put an extra mounting points in, so I can put some extra mounting points in to stop the deflection of the board so much. And yep, that has again, quickly run the analysis, that has an impact. Or maybe the best thing to do would be to glue that component to the board surface itself with some potting material. And that has the best, as one might expect. So Sherlock allows the engineer to go in and understand how to mitigate the problems that he's finding, whether it's a change of components, whether it's moving components around, whether it's adding some sort of potting material or glue to fix components down, or adding extra supports and such like. So Sherlock allows that analysis to be done before you've actually built that first prototype. So this can be then fed back into the design process to create that, if you like, right first time prototype that's going to go through the testing process. So very briefly in summary, Sherlock can provide very fast pre-processing, so it can bring in that data from your existing PCB design tool, and using the libraries that we've got built into Sherlock, and you can add to these libraries and modify them. And in actual fact, we provide a librarian service where you can ship as your bill of materials. We will create the library of Sherlock models for you and send it back. That is a service that we provide for free. And then you can do your analysis, your different types of analysis, and it's straightforward to use the tool. So you can actually have reliability engineers use it, PCB engineers use it, mechanical engineers can all access the tool and understand what changes they make and how that affects the perceived reliability and lifetime of the printed circuit board. So by doing this, it simplifies and it democratizes that finite elements analysis sort of use, because that's what Sherlock uses under the hood. So all engineers can use it, and it allows that understanding of quality and reliability to be communicated up and down through the supply chain. By providing these reliability figures, they can be provided out to your customers, and done that way as well. Okay, and then just one final slide. Sherlock is one of a series of tools that can be used with ANSYS PCB reliability portfolio, if you like. I've already mentioned SI Wave for signal and power integrity, and IcePack. Sherlock can be used to export the 3D model it creates out to IcePack or out to ANSYS Mechanical, and thereby you can incorporate broader concerns, so maybe particular types of housing or special cooling that you want to incorporate, and that information from those tools can then be fed back into Sherlock for a refined reliability analysis. And then there's other tools that Sherlock can go out and share the data with, ANSYS Minerva, Optislang for optimization, and so forth. So it is one part of a package of tools that can help you understand and perfect your PCB reliability design.